Assalamu alaikum and welcome back to the channel. Today we will see how to derive weight update equations for the output layer of a simple neural network. We are focusing on a simple network with two inputs denoted as x1 and x2, two hidden neurons denoted as h1 and h2, and one output neuron denoted as O. The weights between hidden layer and the output layer are denoted as WO1 and WO2. The output is the sigmoid of the linear combination of the weights and the hidden outputs. The linear combination is WO1 times H1 plus WO2 times H2 and vice. In this video, we are calculating how to adjust the three final parameters: the weights WO1 and WO2 and the bias BO. First, let's define the three equations that link our parameters to our error: the loss function, the output activations in terms of sigmoid, and the net output Z. The loss function is 1/2 times y minus O squared. Y is the actual output and O is the predicted output. This is the value we want to minimize. To update the parameters, we need to see how small changes in the weights change the loss. But here's the problem. Our loss function is only directly defined in terms of predicted output O, not in the terms of weights W or bias B. We can't take the derivative of the loss function with respect to W directly. Here comes the chain rule. This mathematical rule tells us that if a function depends on an intermediate variable, we can calculate its derivative by multiplying the derivatives of each segment of the chain. In our case, the loss function is written in terms of O is written in terms of Z, and Z is written in terms of weights and bias. So by using chain rule, we can take the derivative of the loss function with respect to output, derivative of output with respect to Z, and the derivative of Z with respect to weights and bias. We will now calculate each of these three segments individually. We start with the derivative of loss function with respect to the output. We use the power rule. The 2 is multiplied and the power of y minus O is reduced to 1. Then we multiply by the derivative of the inner term, that is y minus O, which is negative 1. Now the derivative of loss function with respect to O becomes O minus y. Next, we take the derivative of the output function with respect to the net input Z. Since it's a sigmoid function, the output of sigmoid would be O into 1 minus O. Now we need the derivative of the net output Z with respect to each parameter separately. That is WO1, WO2 and BO. Let's start with respect to WO1. We treat WO2 times H2 and BO as constants, and H1 is constant input from the previous layer. This term becomes 1 multiplied by H1. So the derivative of the Z with respect to WO1 is H1. Similarly, with respect to WO2, the only term containing W2O remains. So the derivative with respect to WO2 is H2. Now derivative with respect to bias. The term containing WO1 and WO2 are constants. So they are 0 and the derivative of bias is 1. So the derivative of the Z with respect to BO is 1. Finally, we substitute all three derivative segments back into the chain rule equation. So the derivative of the loss function with respect to WO1 is O minus Y, O times 1 minus O times H1. Similarly, for WO2 and for bias. These gradients or the derivatives tell us the direction and steepness of the error. We use them directly in the gradient descent formula to update the weights. WO1 equals to old WO1 minus learning rate times the derivative of the loss function with respect to WO1. Similarly, the weight update equations for WO2 and BO are written. And that in essence is the math behind every single weight update in the output layer of a neural network. Next time we will take this knowledge and use the chain rule again to calculate the even trickier gradients of the hidden layer. If you found this video helpful, please like, share and subscribe for more videos on data science and AI. See you in the next video.